In this video, I'm going to continue discussing the reactions of conjugated systems. So remember, our reactions of conjugated systems are these pericyclic reactions. In the previous couple videos, we talked about the cycloaddition reactions. In particular, we talked about the Diels-Alder reaction. In this one, I am going to discuss electrocyclic reactions. And so this is going to be an intramolecular ring closure or opening. So in electrocyclic reactions, the reactions can be either, like I said, ring opening or ring closing. And these can be done just like with the Diels-Alder reaction under photochemical or thermal conditions. And depending on the type of reaction, whether it's photochemical or thermal, and the number of pi electrons, the reaction can happen through either what's called a conrotatory or disrotatory mechanism, which we'll be looking at in detail here in a minute. And so the type of rotation determines whether the cis or trans isomer of the product will be formed. And so when we're talking about these, we're looking at things like this, where we can either have this ring closed to form this cyclic structure, or we can have it reopen to form the linear structure. So when we form the ring, we can essentially think about this double bond coming to form a single bond right there, and this double bond moving over to right there, so that we end up with this single bond there and then the double bond right there. Similarly, for the 3 pi bond system, we can have this come down here, this move up here, and then this move over here, so that we end up with a single bond right here, and this double bond moved here, and this double bond moved there. Then the ring opening is just the reverse of that. And then when I talk about the conrotatory or disrotatory, what I'm talking about is the way that these orbitals actually rotate, and specifically the orbitals that are going to be forming the sigma bond. So if we have this butadiene here, if we are in the thermal conditions, so that's what the triangle means, then the highest occupied molecular orbital is the pi 2. Remember, that looks like this. So this is the pi 2 right here. So in the thermal conditions, then that is in the ground state. And so this one and this one at the ends are pointing in different directions. So remember, when we want the bond to form, we need to have these orbitals in phase. And so in order for this to be in phase, then this one would have to rotate this direction. So that's rotating counterclockwise, and this one also would have to rotate counterclockwise. That's why it's called conrotatory, because they are rotating in the same direction. And in particular, we're talking about whether it's counterclockwise or clockwise. When I first learned this, to me, I always wanted to think, well, if they are both rotating where the lobes are both going inward, such as what we see up here, where this one's going to go inward there, and this one's going to go inward there. To me, my mind always wanted to say that that means that they're rotating in the same direction, but what we want to keep in mind when we're talking about the direction is whether it is clockwise or counterclockwise. So for the conrotatory, they are both rotating in the same direction. And so as these rotate in the counterclockwise direction, they are going like this. So we end up with them slanted like that, but then they end up pointed at each other. So we can have this constructive overlap going on here. Similarly, for the disrotatory on our butadiene, now we are in light conditions, and so we have to look at the pi 3 star there. And so if we look at this over here, so now this is our highest occupied molecular orbital. We see both of these on the outside are going to be pointing in the same direction. And so in order for these to have the constructive interference, one has to rotate clockwise and the other one counterclockwise. Again, we end up here, they're continuing to rotate this way, and we get over here where we can have the constructive overlap. In the cases shown here, this looks like it doesn't really make that much of a difference, but where it does make a difference, as we'll see here, is when we have other substituents on it. In general, the Woodward-Hoffman rules for this, for the thermal and photochemical conditions, and these are for the ring closures in particular, if we have an even number of conjugated bonds in our system, then the thermal condition will have conrotatory and the photochemical will have disrotatory. If we have an odd number, then the thermal conditions will be disrotatory and the photochemical conditions will be conrotatory. And so those end up being opposite depending on whether we have an even number or odd number of double bonds in our conjugated system. And so this looks like for our butadiene here, when we do the disrotatory, so again, we have to do this under photochemical conditions, we end up making this right here. And so we have these rotating in opposite directions, that's disrotatory. But if we are looking at our hexatriene, then we see that it's in the thermal conditions, when it's in the ground state, if we look back over here, that this is when these two lobes on either end are pointed in the same direction, and so that's when we will get the disrotatory. So these have to both rotate in opposite directions in order to get that constructive interference, that overlap, and so that's how we will get the ring closure. Whereas conrotatory, now we have to have thermal conditions for the butadiene, that's the one with an even number of double bonds in the conjugated system, and so this one, these will be rotating in the same direction, and so that's what will give us the ring closure in thermal conditions for the butadiene. For the hexatriene, now we have to have it in light conditions. So we look at our pi 4 star over here. So this is where we end up with these in opposite directions on either side of the system. And so that's going to give us the conrotatory for this one. So these ones are rotating in the same direction. That will give us the ring closure. And so like I said, why this is important is if we have other things on either end of our conjugated system, so other substituents, such as having a methyl group on either end right here. And so what we'll see is that if we do this 2-pi system under light conditions for our trans 2,4-hexadiene, then this is going to rotate this way, and this one's going to rotate that way. So they will be going disrotatory. And so what we see is if those are rotating that way, then this is going to get flipped upward, and this one is also going to get flipped upward. And so we end up with a cis stereochemistry right here. Whereas if we do this under thermal conditions, now we see this one's going to rotate this way, and this one's going to rotate that way. And as this one on the right rotates that way, this will get flipped down, and as the one on the left rotates clockwise, this will get flipped upward. And so we end up with the trans stereochemistry for it. Now, if we look at this where we have the methyl groups pointed outside here and then inside right here, now if we do the disrotatory, so this one's rotating inward, as is this one right here, this is going to get flipped upward and this is going to get flipped downward. And so we end up again with the trans stereochemistry here. Whereas if we do this under thermal conditions, this is rotating down that way, this is rotating up that way, so we have the conrotatory, this is going to get flipped downwards, and this is also going to get flipped downwards. And so we end up with the cis stereochemistry here. Now, if we look at this for our 3-pi system, we'll see that we end up with essentially just the opposite. Whereas if we have the thermal conditions, this is going to be disrotatory, that goes down that way, that goes down that way, and so this gets flipped up that way, and this also gets flipped up that way. And so we end up with the cis stereochemistry. Whereas if we do this under light conditions, we have a conrotatory reaction, and so this will get twisted down that way, this will get twisted up that way, so it'll end up flipping this upward, and this will end up getting flipped downward. So we end up with the trans stereochemistry for that. Whereas now, if we have one methyl group pointed in and one out, we have the disrotatory, this will get twisted down that way, this twisted down that way, and so this methyl group will actually get flipped downward, and this one will get flipped upward, and so we end up with the trans stereochemistry. Now, if we do this under light conditions, we have conrotatory, so this gets twisted that way, this gets twisted that way, and so this will get flipped downwards, and this will also get flipped downwards, and so we end up with the cis stereochemistry for it. With the ring opening, this is just the reverse of the ring closure. So we can see here with this one, when we have the conrotatory, this is going to rotate that way, and this is going to rotate that way. So they're both going in the counterclockwise direction. This methyl group, which is pointed upward, is going to get kind of rotated out that way, so it's pointed out. This one is going to get rotated that way, so that it's also pointed out. And this is something that is very common with these, because we don't want the steric hindrance of the two methyl groups pointed towards each other. They will tend to rotate so that they're pointed out away from each other. If we have the disrotatory under thermal conditions, then this one is going going to rotate counterclockwise, and this one's going to rotate clockwise. That's going to cause this to flip over that way and this to flip over that way, so that we end up with those both pointed out like that. And finally, we can look at how all of these things fit together. So this over here on the right is our table of the thermochemical conditions. And what we see is if we have something like this, so that's the 3 pi bond system. If we heat it up, that causes disrotatory, and we can do a ring closure that will give us this cis right here. Then we can do it under light conditions, which will open the ring. Conrotatory, we end up with this right here. If we heat it up again, that will do disrotatory. We can end up with a racemic mixture here with the ring closure. Then we can use light again to do conrotatory to do the ring opening, and that will give us this right here. Similarly, we can do this for the 2 pi bond system down here. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.